Hey, welcome everybody to another Origin seminar. Today we have Kevin Hardegree-Ullman, who is a postdoc here at Steward. Before that, he got his PhD at the University of Toledo, and he also did his bachelor's in astronomy also right here. And he's also worked extensively with Jesse Christensen at Caltech IPAC, and today he will tell us about hope or maybe not hope for finding oxygen with ELTs. Take it away when you're ready.
All right, thank you. Welcome everybody. I've spent about the past year, also let me know if you can't hear me. I've spent about the past year and a half trying to figure out if we're actually going to be able to observe oxygen with the upcoming extremely large telescopes. So stay tuned for the answer. Also, on every single slide, I have a link to the paper that was just accepted to the Astronomical Journal. It's up on archive, so check it out for more details. And my wonderful collaborators are listed here as well. So just some very basics. On Earth, we know that oxygen is created largely through the photosynthesis process. Here is just a cartoon example with sort of the chemistry on the bottom here. We have the plants are sort of absorbing carbon dioxide. They take in water from the ground. You add a little bit of energy from the sun, and that can spark this little chemical reaction that just strips away the carbon from the carbon dioxide and leaves you with some wonderful oxygen that we all breathe. Very basic. It's a little bit more complicated than this, but this will just give you a picture that oxygen as we know it comes largely from the photosynthesis process. So could we use that to maybe find life out there? Another just background basics. I am talking about transmission spectroscopy throughout this talk. This is just one of the methods that we could potentially use to detect oxygen on an exoplanet. And so in this video, it's just a very simplistic way of looking at things. If we put a spectrograph on a telescope at a star, we'll get a nice spectrum of that star. If the star has a planet that crosses in front of it, we can actually peer through the atmosphere of that planet, giving us, again, another spectrum. If we take the spectrum of the light from the star and the planet combined, subtract the signal from the star, we get a nice spectrum of the planetary atmosphere itself. And then we can go in and identify what signatures are within that atmosphere. And we've been able to do this with a number of planets, not quite at high resolution enough or good enough for Earth-sized planets yet, but we're getting there with atmospheres. So those are some basics. We also know that Earth's atmosphere has evolved over time. This is a very nice diagram showing roughly how we think the Earth's atmosphere has evolved over time. The early Earth had a lot of carbon dioxide and methane for the first 1.5 billion years. Then something happened at about 2.5 billion years ago. Cyanobacteria in the oceans started photosynthesizing and generating enough oxygen to displace that carbon dioxide methane atmosphere. So since 2.5 billion years ago, we've had an oxygen richer environment, and that has allowed or aided in the evolution of more complex life. Then about 500 million years ago, we started to get things like plants on land, animals on land. And so we add more complexity to the scenario. But here's an example of a modern Earth spectrum, a bit more of a signature of O2. If you see right here, the sort of right when oxygen was being formed, there's a small signature, but there's a much larger signal today. And then there are other potential biosignatures. We've got water, we've got methane, and it's interesting to see just the difference. When I'm talking through this through this talk, we mostly, we exclusively looked at sort of a present day Earth-like atmosphere for searching for oxygen. So you can model different stages of Earth's evolution, but for the purposes of our work, we looked at a modern day Earth atmosphere. We know that oxygen is a strong indicator of life on Earth because of this photosynthesis process. But this is just a nice example showing that we've actually looked at Earth's atmosphere from space. This is from in 1990, we sent the Galileo space probe out to go look at Jupiter, but on its way, it took a peer back at Earth and noticed this whopping O2 signature at about 0.75 microns. And basically oxygen and methane in extreme thermodynamic disequilibrium in our atmosphere is sort of an indicator that we can use to go probe for biosignatures out on exoplanets. I'm not going to talk about other potential biosignatures, but it is very important work. We do need to observe other biosignatures to really conclude that we have detected a biosignature on other planets. That's because there are abiotic processes that can create oxygen on Earth. So we need to rule out if this is a biological process or a non-biological process. For example, there's water, methane, CO2, ozone. But a lot of these biosignatures can actually be observed with facilities like JWST. These plots show the magnitude of the star. These are examples of nearby M dwarfs, the distance to the star, and then the number of transits required to detect I believe, 3 sigma detection of these other biosignatures. So you need fewer transits if you go toward later type M dwarfs. As you get further away, obviously it takes more transits to detect. But for example, a 10 parsec planet, a 10 parsec Earth orbiting a mid M dwarf will take on the order of 10 or fewer transits to get a signature of most of these biosignatures. It turns out ozone is probably the harder of the molecules to detect. But there are other ways to detect these other biosignatures, so I'm not going to talk about those. I'm going to talk exclusively about oxygen. But oxygen cannot be observed or detected by our friend JWST. Not enough light collecting area. Also, potentially, you can't do it with transits with a small aperture like this. But I will discuss other ways that we can actually use to detect oxygen. Luckily, within hopefully the next decade, we have 3 very large ground-based telescopes coming online. These extremely large telescopes, starting with on the left here, the extremely large telescope, or the European extremely large telescope, the EELT. In the middle, the 30-meter telescope, the TMT, and then the UA. The project that UA is very involved with, the Giant Magellan Telescope, or the GMT. These are some high resolution spectrographs that are planned to be like first generation instruments that we could potentially use to probe for Earth-like levels of O2 with these facilities. Their previous studies did search, basically do an analysis, could we detect biosignatures with these ELTs? However, these previous studies did not fully consider things like planet occurrence rates, how common are Earth-like planets around other stars. They did not fully assess target observability. If we're looking for transits, they have to be transiting when it's visible from a ground-based facility, so we have to account for that. But probably the major effect is we're looking through a terrestrial atmosphere with our own biosignatures. And so we have to have a relative system velocity offset to be able to not be confused with our own terrestrial signal. So we have to consider the relative system velocities at the time of observation. So all of those factors have to go into simulating these biosignature detections. So a little bit more about the oxygen blending. These are example high-resolution spectra of two different oxygen bands, the O2A band and the O2 near-infrared band. And you see a bunch of lines here. The top is basically an exoplanet Earth transmission spectrum. The middle here is what our atmosphere looks like, our terrestrial signature. And then the bottom is the signature of the star. And so if we observe the star when a planet is not transiting in front of it, we can get very easily this stellar spectrum and remove that from the picture. However, these lines have to be offset enough for us to not confuse them with each other. So they need to be shifted. So the geometry has to be just right for us to not confuse the signal with our own terrestrial signal. And so that's where line blending becomes an issue. At certain relative radial velocities, we can't actually observe oxygen on other planets. And so previous studies have said, oh, best case scenario, we observe when the fraction of blending is lowest, and we'll just run with that in our simulations. They didn't consider sort of the full picture, but when there's no radial velocity offset, you really can't do this. They're both for the A band and the near infrared band. There are some regions where it's not an ideal situation to observe. So you have to be at these regions where the effect from line blending is minimal in order to observe it. And so this is where our Bioverse framework comes in. Bioverse is a sort of statistical framework to run simulations of exoplanet systems. This was developed by former UA grad student Alex Bixel, along with Daniel Pai. And I'm not going to go into detail about this, but it's a very modular system where you can have different inputs, simulate different surveys, and then run hypothesis tests. And so I'm mostly going to talk about module 1, where we generate planets, and then module 2, where we run a survey simulation. But up here at the very top, exoplanet astronomers specifically need to not forget about the stars. The stellar characterization is very important, and especially when you're talking in a statistical sense, you have to have very good uniform stellar parameters. So the first thing we did was use this wonderful data from the Gaia mission to uniformly classify about 287,000 main sequence stars within about 120 parsecs. These are pretty much all of the stars that we would possibly use for targets for upcoming exoplanet missions to study the planets in detail. And so here I'm showing color magnitude diagrams using the Gaia photometry. Gaia has 3 band passes, the Gaia G band, which is a very broad optical band. Then it has a blue and a red band, sort of separating the two. You'll notice in these color magnitude diagrams in the one on the left that there's this hook feature toward the later type stars. This is not a real effect. This is just that for intrinsically red targets, the blue band is not very good. So we go to the Gaia G minus the red band, and we have less of that issue. We have an issue up here with some flux excess that I'm not going to get into, but for targets that are brighter than an absolute G magnitude of about 13.5, we use the blue minus red colors to help classify the stars. And for targets below that, we use the G minus the red color. And so we were able to create a uniform photoastrometric catalog of these main sequence stars, getting the temperatures from these colors in absolute magnitudes, using, again, basic astronomy, luminosities from absolute magnitudes and accounting for bolometric corrections. We got the radius from the Stefan Boltzmann law, and then masses from mass luminosity relations. So with just some basic astronomy knowledge, you too can build a wonderful catalog using Gaia data. And so we tested if our stellar properties were in the ballpark of other measurements. These turns out to be in very good agreement with measurements of known exoplanet hosts. These are our temperatures, radii, and masses compared to these known hosts for the same values. And so the histograms are for our temperatures up here, and overlaid on our temperatures is the side histogram over here. So we're in very good agreement to within about 1% for temperature measurements on average, 3% for radius measurements, and 5% for mass measurements. And those are basically statistically within 1 sigma in general. So we're getting very good agreement on those. I'm going to focus on the 20 parsec sample and largely focus on the 20 parsec sample of M dwarfs. These histograms show the distribution of stars within 20 parsecs in their different temperature ranges. And you'll notice that a majority of the stars are these M dwarfs. And specifically, we peak at mid M dwarfs. We're mostly M dwarfs nearby. And so those are very good targets for more than just the numbers reason. But also mid to late M dwarfs are very good candidates for habitable zone follow-up. And so in this diagram, I have orbital period on this axis versus spectral type with the larger stars up here. And then we have the habitable zone from the Kaparapu definition of habitable zone. And in these tables, we show geometric transit probability toward later type stars. You have up to a roughly 2% geometric transit probability, so you have a better chance at finding a transiting Earth around later stars. But also the orbital period for a habitable zone planet is much lower. The transit duration is shorter, and you have access to a lot more transits per year. So going toward mid or later M dwarfs is actually ideal if you're looking for oxygen in transmission. And so I talked earlier about considering for a survey this eta Earth value, the number of habitable zone Earths that we expect nearby. And unfortunately, this eta Earth value is very poorly constrained, largely because most eta Earth values are from Kepler mission. And Kepler, unfortunately, didn't really observe that many Earth-sized planets in the habitable zone of their host star. And so our constraints on this eta Earth measurement are extrapolations at best, but we do have a range of literature values between about 5 and 35% in general. And so these simulations show the distance and then the cumulative number of Earth-sized habitable zone planets that we expect. So for the range of these values, for transiting planets, we don't necessarily expect within 10 parsecs there to be any transiting habitable zone Earths in our sort of best case scenario from just assuming 35% case for eta Earth. However, we know from just general planet occurrence rate studies that M dwarfs are more commonly, they more commonly have Earth-sized planets around them than FGK counterparts by a factor of about 3.5. So if you take the raw numbers of these eta Earth estimates, multiply them by 3.5 for M dwarfs alone, the case gets a little bit better. So maybe we can expect one or a couple up to 10 or 20, maybe in our very most optimistic scenario within 20 parsecs, habitable zone Earths. So this sort of establishes that we can expect to find habitable zone Earths nearby, but it's not terribly likely in even some of these optimistic scenarios to find one within 10 parsecs, which would be ideal for transmission spectroscopy. But I'll talk more about that later. Next, we have models of the number of transits that we need to probe Earth-like levels of O2 with these ELTs. And so this is the extent of what most past work has done. They show you these models of telescope diameter versus number of transits needed. And this is for a mid-M dwarf, and these different curves are for different distances. And then these lines show the effective telescope diameter of, say, the GMT, the TMT, and the EELT, and then hypothetical larger aperture telescopes from 50 to 100 meters. So for example, if we had a 10 parsec, an Earth orbiting in the habitable zone of this M4 star at 10 parsecs, it would take about 100 transits to do this with the GMT. A little bit better with the TMT and ELT, but it's still going to take a lot of transits to do this kind of work. Much larger aperture telescopes would be able to do this in fewer than 10 transits, closer to 5 transits if you had a 100-meter telescope. What we did here was use some of that information that I showed in the previous slide. We basically populated every M dwarf within 20 parsecs with a habitable zone Earth-sized planet. And then we calculated how many transits are observable on average for these nearby planets. And this is what we get. When we don't have to worry about relative system offsets, we get this maximum number for the GMT, TMT, ELT, and then just sort of if you can combine the signal from all of those, this is what you get. If you have to worry about offsets from this simulation because of the O2A band to mitigate this line blending effect, your numbers are cut in half. It's a little bit more optimistic for the near infrared band. If you observe both bands simultaneously and wanted to get signal in both, you have it's sort of less optimistic than the O2A band. Then there's sort of an optimal band situation. Sometimes it's you can observe in the A band, sometimes you can observe in the IR band. So if you had a spectrograph that was able to access both, this is kind of your optimal scenario. But then when you account for geometric transit probability, your numbers tank. So you have about 10 or fewer targets that you can potentially target. This is assuming that we need to observe a full transit with some baseline. However, a more optimistic scenario is if you only need to observe a partial transit, because for transmission spectroscopy, technically all you need is some baseline measurement and then an in-transit measurement to get sort of the difference of the size of the planet atmosphere. And so your situation improves if you only need partial transits, but you're still killed by geometric transit probability. So the likelihood that the planet is in transit. So let's run our simulation. Now that we have all of the components in place, let's run a simulation. So we randomly drew a value for eta Earth for M dwarfs. We sort of have that range that I discussed earlier. We do have a measurement for eta Earth for M dwarfs from the Kepler mission. It's not very robust, so this is a potentially tunable parameter, but we generate a set of habitable zone Earths from this eta Earth estimate. Then we determined which Earths are transiting and if O2 is observable at the simulated time of transit. Then we calculated how many years it would take to probe Earth-like levels of O2 at 3 sigma. And then we repeated this 10,000 times in our simulation. And then once we have all of those simulations, we basically created 10,000 separate universes of just a handful of planets, from 0 to 13 planets based on our value from eta Earth. And so we can sort each universe by the number of years it takes to probe O2, and then take the lowest number and sort of get the average number of years for that for our simulation to say this is how many years we think it would take to probe O2 for just sort of the average first planet with the smallest number of years in our simulation. And this is what we get. These are the different colors, and different dashed lines are for the different extremely large telescopes. It'll take forever if you just use any individual ELT. If you can somehow combine the signals from all of the ELTs, it'll still take a century from our simulations to probe O2 on one planet. This is from 1 to 8 planets. If you had much larger aperture telescopes, your situation improves, but the situation is looking grim right now. However, that was assuming a full transit scenario where you need the full transits. Let's go to our partial transit scenario. It's a little bit more optimistic, but even if you could combine the signal from all of the ELTs, it'll still take 60 years. The estimated sort of operational and supported duration of these ELTs is about 50 years. So you wouldn't necessarily be able to do this during the operational lifetime of the ELTs. However, if you could build, those simulations assumed an R of 100,000 spectrograph. That's kind of the first generation of spectrograph that is currently being built for these telescopes. If you could build a spectrograph with a resolution of 500,000, you might be able to improve your situation. At R of 500,000, your O2 lines are narrower and deeper, and you are less affected by blending. These simulations sort of show the difference between an R of 100,000 and then an R of much higher. So above 500,000, you don't really get much improvement, but you do have narrower lines, and you're also less affected by blending, especially at this near IR. That means in your simulations, you have a little bit more leeway for where lines are blended. So if you go up to an R of 500,000, that again reduces your time by another factor of 2. Now you're talking about maybe 25 to 30 years for probing oxygen on one planet, which still is not really the best scenario. However, these are simulated planets in a simulated bunches of universes. Are there any known planets nearby that we can potentially search for O2? And I would be remiss if I didn't include a plot like this in an exoplanet talk, where we have orbital period versus planet radius in terms of Earth radii. And then I have the solar system planets plotted over here. Most of the planets on this diagram, at least, are nowhere near Earth. And then the different symbols indicate the different techniques that we use to discover them. But when we're talking about biosignatures and potential habitability, there's maybe a different metric that we can use plot on this x-axis to give us a better picture of what's going on. And so on the x-axis now, I plot this versus planet temperature due to the parent star in terms of degrees Celsius, because on the Celsius scale, a very, very loose definition of our habitable zone is where liquid water can exist. So between 0 and 100 Celsius on Earth is where liquid water can exist. And so, but we know that it's a little bit more complicated than this. We have Earth and Venus here. Venus would be a bit hotter just due to the parent temperature of the star. Anyway, let's draw a box where we think potentially Earth-like planets could reside. Between minus 100 Celsius and 100 Celsius, and then a minimum sort of where rocky planets could retain an atmosphere, and a maximum near where the planet radius valley is, where we think that rocky planets become more like Neptune. And so let's zoom in here. And now I've colored the points by the temperature of the host star, and you'll notice that most of these planets in this box are around M dwarfs, cooler stars. Then we have Earth and Venus here. But are all of these observable? Probably not. Let's limit ourselves to our 20 parsecs that we were talking about earlier. And the number is drastically reduced. And it just so happens that these planets come in two star systems. We have our lovely TRAPPIST-1 system and then LHS 1140. And for the more complicated reasons, the planets over here aren't actually in the habitable zone of their host star. But these planets are. However, LHS 1140b might have sort of too thick of a hydrogen atmosphere. It might sort of hide oxygen from below. So we're not going to talk about LHS 1140b right now, but there are 3, maybe 4 planets in the TRAPPIST-1 system that could be in the habitable zone. So let's take a look at those. So let's rerun our simulations like before, but considering these real planets in the TRAPPIST-1 system, if we again somehow combine all of the signal from all of the ELTs, it'll still take 25 years to probe oxygen on TRAPPIST-1d. Everybody's more favorite habitable zone planet is TRAPPIST-1e. It'll still take 35 to 40 years. Again, all of the numbers in here I would actually consider as lower limits because we aren't fully considering red noise in our simulation. So take these as lower limits. So these are very optimistic. Again, this is the full transit scenario. If we only need partial transits, it's a little bit more optimistic, TRAPPIST-1e in less than 25 years. And then if we go to a much higher resolution spectrograph, now we're talking maybe 10 years if we get the partial transit scenario with the R500,000. So this might be possible. I'm still not totally optimistic though, because we have to combine a lot of different signals from different instruments. And we're still not considering the full picture, but we are considering the full sort of observability aspect of these planets. So what are our other options for potentially observing O2? Well, we might be able to use direct imaging and get a reflected light spectrum of the star. Some work has been done, particularly using the VLT, which is an 8.2 meter telescope with an adaptive optics system where we can block out the light of the star sphere, and then a high resolution spectrograph espresso. These would require a few upgrades to be able to do this kind of work. But this previous work basically took different types of atmospheres. So it would take a very long time to detect the atmosphere of a dry planet with CO2. If we had an Earth that was in a synchronous orbit, so I think just a tidally locked where one side faces the star at a time, it would take a lot of hours. If we had more of a resonance, like a 3-2 resonance, it's a better scenario, and it would be fairly easy to rule out a Venus-like atmosphere. But they did simulations for Proxima Centauri b, which is a known planet within at 1.3 parsecs. And they said it would take about 60 nights or about 3 years, 3 observing seasons for a 3.6 sigma O2 detection on just the VLT. So that sounds fairly promising for our extremely large telescopes. We have a lot more light collecting area, so this might be another option, and it's something we will be exploring next. Another option would be to go into space. In space, you don't have to worry about our own atmosphere, so it's already simpler, but we know that JWST won't be able to do this. But the Habitable Worlds Observatory is a direct imaging mission, and with a goal of detecting biosignatures on about 25 planets. But there's also, from Daniel Pai, this concept, the Nautilus Array, putting a bunch of diffractive optics lenses into space at 8.5 meters that can be dispensed like PEZ. And these platforms sort of inflate. And from their simulations, you have 8.5 meter aperture lenses, and they say using one lens, you could detect oxygen on a 15 parsec M dwarf Earth within about 30 transits. And so that's pretty promising for just one lens. If they had the full 35 element array of these telescopes, we could potentially detect biosignatures on 1,000 Exo-Earths from their simulations. So that's kind of neat. So here's kind of a hypothetical timeline to be able to probe Earth-like levels of O2. We're sitting at here today. The ELTs are expected to come online early 2030s-ish. By 2040, somewhere around 2040, they expect the Habitable Worlds Observatory to launch. And also there's another concept telescope called the Large Interferometer for Earth that's expected to launch around 2040. That observatory won't necessarily be able to detect oxygen, but it will be looking for other biosignatures like methane and CO2, I believe. And then there's also a concept for the Large Fiber Array Spectroscopic Telescope that Roger Angel has developed, which is a bunch of, I think, 0.75 meter telescopes on the ground, build a lot of them in mass, and you get a large collecting area, combine all of the light from the fibers. LFAST survey could happen mid-2040s if we get things building. But also the Nautilus project that I was talking about launches, is expected to launch about that time too. And so those are potential avenues to search for O2. By 2050, Habitable Worlds Observatory is expected to image 25 Earth-like planets. From our own simulations, the ELTs might be able to use transmission spectroscopy to get oxygen on 1 to 3 planets, maybe. By mid-2050s, maybe LFAST could get a few more planets in transmission spectroscopy. And then if Nautilus launches by 2060, again, we're thinking about the whole career lifetime of a young astronomer in this room for O2 detection on hopefully a handful to dozens to hopefully thousands of exoplanets. One caveat that I haven't fully looked at in my own work is that satellites and satellite constellations specifically could pose a severe threat to this kind of work. We know that a lot of things just in the past couple of years have launched. Thousands of these satellites have launched, and they're already causing issues for astronomy and especially ground-based surveys. Interestingly, recently, the LMOST survey team, they're getting mid to high resolution spectra of millions of stars. They actually identified a bunch of spectroscopic binaries, but the spectroscopic binary component is at 0 radial velocity offset. So it turns out that signal is actually coming from reflected light off of satellites from the sun. So they're expected to have about 20,000 Starlink satellites by the time that the ELTs come online. And then there are also thousands more that are going to come online from projects like OneWeb and Project Kuiper. So this is something that's potentially a threat. In positive news on that regard, all of these extremely large telescopes will be most likely using lasers for their adaptive optic systems. There is recent news about normally you have to turn off your laser when satellites are passing overhead. You have to say, this is what we plan on observing and when, and schedule all that when your laser is going to be on. Lasers will not have to be shuttered during the passing of Starlink satellites. So that's one positive aspect, but there's still potential for satellites contaminating your images in spectra. Yeah.
Well, I just want to say that that's not a world rule, that's a US rule.
Yeah.
So that means that telescopes in the Southern Hemisphere don't have to do that.
Awesome.
That's all. It's only the telescopes in the US that have to do that.
Okay, so the TMT is going to be affected, but maybe not the GMT or ELT. Cool. But still, satellites might still be an issue for other reasons. So in conclusion, we did a comprehensive assessment of using ELTs to probe Earth-like levels, current present-day Earth-like levels of O2 via transmission spectroscopy. including aspects of planet occurrence rates, target observability, and relative system velocities. And I'm going to say that I think it's extremely unlikely that transmission spectroscopy is going to be the avenue to detect O2 on an exoplanet. It's going to take a long time, and even in our best case scenario, just combining signals from a lot of different data sets, a lot of different telescopes, this isn't necessarily the best route to take. Unless we have better targets, if we find a 5-parsec Exo-Earth transiting around a late M dwarf, that would be fabulous. Or if we build even bigger aperture telescopes, or maybe the most simple of the three is just building a higher resolution spectrograph. But maybe you need a combination of all of those. And so possibly direct imaging or space telescopes, large aperture space telescopes might be better suited for O2. And with that, I will take any questions. Yeah.
I have lots of questions, but I'll refrain. So first, I think I'm hopeful that your timeline for LFAST is off by a decade.
Yeah.
The relative system velocity thing is a really interesting component of this that I think hasn't really touched well before. So what, maybe I missed it, but what was the distribution of systemic velocities that you used for your sample? And did you do realistic barycentric throws throughout the year and can all that in?
Yes, we threw all of that in. We used the radial velocities of all of the known planets, known systems. We used real RVs, and then we used I think a large fraction of ours didn't actually have RV measurements, so we figured out a way to actually assign RVs to those targets using machine learning. And so a lot of them are sort of assigned, but based on sort of a large sample of realistic radial velocities. So yeah, we threw all of that into our observations to get a realistic observing scenario.
So does that mean then that we need better analysis techniques to be able to more closely separate exoplanet oxygen from terrestrial oxygen and smaller relative offsets?
I think based on the...
Because you had like something like 50 kilometers per second, which is just about.
Yeah. Better. Yeah, so plus or minus about 10 to 20 is where you're really screwed. These wings over here, you will have a significant fraction of blending, but if you see the sort of background level of blending, you're going to have to mitigate that somehow anyway. So the main concern is if your relative velocities are near zero.
I sort of have a similar question about oxygen blending. I was wondering if you can model the terrestrial oxygen spectra or just subtract it off to get the answer somewhere.
I don't think so. I think it's really tough if you're just overlapping in these O2 lines to really conclusively model out your own Earth atmosphere and say the leftover component is the true signal from the planet. I really think you do have to have a significant enough offset to really distinguish between terrestrial versus non-terrestrial.
Yeah. We can do the Zoom question first.
Would you like to unmute Paul and ask your question, or would you like me to read it?
All right. Well, thanks for the talk and the paper. It looks great. My question is very quick. Have you considered exomoons?
In what sense?
Well, for this type of a spectroscopic study, obviously the problems are very different when it comes to exomoons, but So
So, like,
That's the
for
question.
example, trying to detect oxygen on an exomoon orbiting like a Jupiter-like planet in the habitable zone, or
yeah, or anything else for that matter.
yeah, I have not considered that. That would be kind of neat, but then you have, especially with via transmission spectroscopy, you have to have the planet moon system also being in a really good alignment too. So that would add another level of difficulty. It would be neat, but I think first step in that process is actually conclusively finding an exomoon. Yes, Sebastian.
You tried different spectral resolutions. Do you know at what spectral resolution it's the gain sort of stops?
So this paper from Lopez Morales basically said that the gain stops at R 500,000. If you go to R 1,000,000, that's effectively useless. There are sort of minimal gains between R 300,000 and 500,000. You do get narrower and deeper lines, but then when you disperse the light out more, I'm not sure if spreading out the light more is going to affect your signal too. So from this paper, at least, they said R 500,000 is kind of your optimal range. Yeah.
You can quantify the gain as a function of resolution. If you go up from 100,000 with alphas, we think we can get the cost of collecting the light low enough so the spectrograph starts to be a significant fraction of the cost. So looking at the gain, going 100, 150, 200, if we put a dollar value on that, we can decide whether it's better to build more telescopes at lower resolution or a smaller number at a time.
I do have a question about LFAST though. When you're combining the signal from all these small aperture telescopes, like how much of an effect do you have from just multiple instrument noise and combining that signal? That's maybe my biggest concern about combining this from several different sources.
Yeah, if you could quantify that would be good. Certainly we focus obviously photon noise is primary because we can't get around it.
Yeah.
But in these various papers in Snell, people have looked at the red component of noise. I don't see it as fundamental. And we've got sort of complete control of what happens to the light and how we deal with it. So.
Right. Everything.
Online, Everett has a question.
Yeah, excellent talk. I was wondering how optimistic you are about doing the high resolution and direct imaging, so you get spatial separation and spectral separation of targets. I think that's been one of the hopes for GMT that I've seen.
That's interesting. I haven't really considered that, though I feel like transiting systems are probably one of the least ideal to do the direct imaging for, and vice versa, because one is reflected light, and so you need the planet to be in a geometry that's reflecting enough light. I haven't fully considered the scenario though, but my guess is that they won't necessarily work in tandem. And I think Brittany had something.
So I'm not familiar with a lot of RV stuff. So the footprint of GPLET, is it big enough where you can get other molecules for free? In terms of, because like O2 is not the only molecule to study, right?
Yeah.
What are some other questions we can hopefully answer with spectroscopy?
That's a very good question. Transmission spectroscopy will be phenomenal with these ELTs regardless, not necessarily for detecting biosignatures on other Earths. I'm not familiar with the wavelength range you'll get at R of 100,000, but I'm sure, I think other studies recently have actually discussed using the ELTs to get like methane, CO2, other things, and those are actually a bit more promising than O2 detection. But I still think the observability scenario is another factor that needs to be thrown into there.
You talk about similar to the micron.
Vladimir online.
Yes. Hello. Yeah. Unfortunately, I joined a little bit late today, so for the last like 10 minutes. So probably I missed some. And my question is that why? So you probably expect like 1 bar atmosphere and like oxygen amount like in Earth atmosphere, right?
Yes. Yes.
So it looks like it. Yeah, and we know that our planet acquired oxygen, at like around 21% of the last might be, few 100 million years. It's basically less than 10% of the history. So how
Yes.
can we justify this high amount of oxygen in the atmosphere? In the first place, so why do we expect oxygen? Might be Earth is a, some kind of a just a strange planet, and we're at that kind of evolution, of life. So, which is sculpted by the internal processes and the evolutionary history of our sun.
Absolutely. One aspect is we have very poor constraints on ages for most stars. And so we can't actually quantify the full evolutionary scale. So we have to start somewhere. So in our simulations, we considered an Earth-like atmosphere, modern Earth atmosphere. A few other papers have considered sort of an earlier Earth oxygen atmosphere and then pre-oxygen atmosphere. I think those situations might be slightly easier to rule out the oxygen abundance, but in lieu of doing extensive extra modeling for many different scenarios, I think also one complication is our best planets for searching for oxygen are around these M dwarfs. And it's not yet even clear that M dwarfs can either retain an atmosphere or allow for the evolution of Earth-like oxygen levels. So that's something that hopefully maybe JWST and other facilities will tell us in the near future whether or not this is even worth pursuing for planets around, say, M dwarfs.
Mm-hmm. Yeah, thanks. Yeah, I just want to add that, for instance, for planets around M dwarfs, the thermal escape will suggest that the oxygen will accumulate. However, as we know from our Earth, upper atmosphere, every time we have a flare or we have the strong UV emission, enhancement of the UV emission, we have ionization of oxygen. So dissociation of molecular oxygen into atomic, and then ionization of oxygen. So O+ escapes pretty well, so basically, and approximately scaled with the flux of UV emission. So basically, which suggests that if we assume non-thermal escape, then oxygen also goes away. If we only in our models assume thermal escape, then oxygen accumulates.
Yep. And this can get very complicated very fast. So we only considered modern Earth in this situation, but there are lots of little nuances.
Right.
But I didn't want to write 100-page paper, so.
Other questions? Anybody else online have a question? If not, thank Kevin again for a really great talk. Gordon.